Training models at the frontier requires tens of thousands of GPUs and moving massive amounts of data, creating immense physical compute bottlenecks. Moonshot AI has bypassed these traditional limits with the release of Kimi K3, a 2.8 trillion parameter open-weight model. This is the front-end Code Arena leaderboard. Kimi K3 currently holds the first-place position globally with an ELO rating of 1679. Looking lower on the board, K3 has displaced the previous proprietary leaders, Claude Fable 5P and GPT 5.6 Sol. At 2.8 trillion parameters, K3 dwarfs recent open-source models like DeepSeek V4 Pro, which peaked at 1.6 trillion, and GPU's GLM5 series. To understand how a model this large operates, we have to look at its quantitative benchmarks, its unique token economics, the underlying architecture, and its strict integration requirements. For 3 years, the open-source ecosystem has operated 6 months behind proprietary American labs. With K3, frontier-level intelligence is now openly available. The capability gap closes most noticeably when evaluating real-world software engineering. These are K3's coding benchmarks. It scores 67.5 on DeepSWE and 61.2 on FrontierSWE. Moving to terminal orchestration, K3 achieves 88.3 on Terminal Bench 2.1 and 77.5 on Program Bench, proving its ability to navigate complex repositories. This capability extends into visual environments, utilizing a native vision-in-the-loop feature tailored for front-end UI and game development. K3 natively ingests live screenshots, using visual feedback to iterate on 3D shaders and code without requiring human prompting between steps. Moonshot tested this autonomy by giving K3 its own kernel code and a single directive to optimize it. Over a 20-hour period, with zero human intervention, the model achieved a 2.48x speedup on H200 hardware. K3 operates as an integrated engineering system that continuously validates its own outputs against the specific constraints of the codebase. Despite these capabilities, early professional feedback labeled K3 as prohibitively expensive for an open model. This chart compares raw API pricing. At $15 per million output tokens, K3 perfectly matches the premium tiers of Anthropic's Sonnet and Fable models. However, K3's high reasoning density means it requires up to 21% fewer output tokens to complete complex engineering tasks. When we view this secondary chart and adjust the metric from cost per token to cost per task, a representative engineering job that costs $1.30 with Fable 5 costs approximately 25 cents using K3. This efficiency is tied directly to K3's default state, which locks reasoning effort to maximum. Routing trivial boilerplate formatting to K3 will trigger deep chain-of-thought processing, wasting expensive tokens on simple work. When applied strictly to high-complexity logic, K3 completes the job in fewer steps, resulting in a significantly lower final invoice. Executing a 2.8 trillion parameter model across hardware clusters requires solving a massive physical bottleneck. During inference, data must move rapidly across fiber optic cables between multiple GPUs in a server rack, which creates severe communication overhead. K3 mitigates this using a highly sparse architecture known as stable latent MOE. Instead of activating the entire network, a token embedding is compressed and routed to exactly 16 out of 896 possible experts. This yields an extreme activation ratio of just 1.8%. By keeping 98.2% of the experts dark during any given operation, K3 drastically reduces the data payload transmitted between GPUs. This specific routing mechanism allows the model to scale its total parameter count without collapsing under its own compute requirements. The second physical constraint is the 1 million token context window. Standard attention mechanisms calculate relationships between every single token. At 1 million tokens, the required memory explodes quadratically. To solve this, Moonshot implemented a hybrid linear attention mechanism called Kimi Delta Attention, or KDA. Instead of a uniform memory wipe, KDA applies fine-grained control, allowing individual memory streams to decay and refresh at varied rates independently. This selective retention directly yields up to a 6.3x faster decoding throughput, even when the context window is entirely full. This is paired with attention residuals, a structural update that groups previous layers into larger logical blocks to relieve the GPU interconnect burden. These two architectural updates turn a 1 million token context window into a usable, high-speed workspace for production engineering. Integrating a model of this scale into an engineering environment requires specific API configurations. K3 enforces strict constraints. Temperature and top p-values are fixed at the server level and must be deliberately omitted from all API requests. For agentic workflows, K3 uses dynamic tool loading. Full JSON tool schemas are inserted directly into the system message array, making them instantly available. To utilize prefix caching, the request must contain a minimum of 256 prompt tokens. Anything lower bypasses the cache entirely. For local deployment, the Kimi K3 CLI installs directly into terminal environments, granting the model direct read and write access to local files. K3 is built for deep integration into developer infrastructure, functioning as an automated contributor rather than a conversational chatbot. An open-weight model of this size introduces the capability for total local control, allowing servers to run completely offline and isolated from external networks. K3 operates as a self-contained system engineered for sustained, autonomous execution, limited only by the hardware running it. Engineering teams deploying it will need to evaluate their infrastructure ROI based strictly on the cost to complete a task, rather than the raw cost per token. On July 27th, Moonshot is scheduled to release the full K3 model weights for public download. At that point, a 2.8 trillion parameter frontier model becomes available for local fine-tuning and deployment, entirely free of vendor API limits and data retention policies. This removes the reliance on vendor-controlled APIs, allowing developers to execute frontier-level intelligence on their own infrastructure.